Okay, the natural next step of discussing the kilometer scale climate model and the kilometer scale ocean model is to look at this idea of the digital twin Earth that has been floated by the Europeans and is funded to be implemented. Europe has a plan on green data for all and this digital Earth, which is referred to as something else. Let me pull it up right now. Go away, go away, go away. Okay, here we are. Green Deal policies, which has green data for all and destination Earth. Okay, sorry about that. So under destination Earth comes the digital twin. A digital twin idea is not really new. You've heard of computer aided design and computer aided machines as concepts that were very hot during the 80s and 90s. They have now morphed into other things, including 3D printing and so on. But industrial processes have always tried to create digital twins of actual physical things they're trying to manufacture, so that you can look at the designs, the consequences, the optimizations, fine-tuning, etc. in the digital world before you implement it on production scale and so on. But the idea has now expanded into things like digital cities, for example. Some urban authorities are developing digital copies of cities as portrayed in this artist's impression. So here are the brick and mortar actual buildings, and here is a digital twin. And you can imagine how much value this can have in terms of looking for traffic patterns, energy transmissions, water supplies, even impacts on circulations of weather and climate, heat island effects, and so on and so forth, if you could try things out in the digital world before you actually implement them. So this idea is obviously very exciting if it can be extended to the Earth itself. And this is a paper from the Europeans talking about the concept of digital Earth. So here we are with the planet, which is now facing climate change issues because we did some unintended experiments, maybe, or maybe we ignored the consequences intentionally along the way in burning fossil fuels and increasing greenhouse gases, land use change, climate change, and now we want to safely navigate the future with guardrail policies like 2 degrees C warming with 67% probability by 2100 and so on. And the efforts of climate modeling, of course, go from weather timescales. Weather prediction enterprise has remained slightly on a different path because it's an initial value problem. It's reintegrated only for a few days, so they can have much higher resolutions than climate models, which are integrated for multiple seasons, multiple years, and of course climate projections, which are integrated for multiple decades or even multiple centuries, and in ensembles, which means you perturb some conditions and keep on looking for various trajectories in which the system will evolve. In the meantime, we are observing the Earth from satellites, from drones, from balloons, from ships, from moorings in the ocean, and so on and so forth, that are constantly being fed into models to initialize weather forecasts and of course to initialize El Nino forecasts and so on. And the climate projections are not so much initialized integrations other than initializing with anthropogenic greenhouse gas or atmospheric concentrations of greenhouse gases and so on. So slightly different problems, but nonetheless human interactions are happening at all spatial and temporal scales. So the digital twin imagines a full model which is ingesting this infinite data that are collected either with fixed instruments or moving instruments from space locally within the ocean, in the atmosphere, maybe even human beings carrying them, like cell phone based instruments, satellite phones, etc. And then you are constantly looking for various what if scenarios as imagined here. It could be about construction, a new infrastructure, could be policies, could be energy, renewable energy portfolios, and so on and so forth. And you want to be able to have some kind of a seamless system where the digital earth is constantly keeping track of the earth at every minute in the digital space, and so that we can always look in details from the digital world what's happening, even as all the data are coming in and being merged with the model to produce this continuous rendition, digital rendition of the earth itself. And then you integrate forward from that for days, weeks, or you do what if scenarios as we just mentioned. So very exciting idea, and they have put money behind it, and it's supposed to get ready in a couple of years, I think. You can look up the project plans. So some of the ideas to be considered: the twin architecture is a step change in Earth system modeling because it combines simulations and observations at much greater spatial scale. So you have kilometer scale globally and hectometer scale regionally, so literally down to 100 meters. There are not only just computational limitations to how low you can go, but also there are some process, like the assumptions you make about turbulence, for example, may not work if you go below 100 meters and so on. So one has to also be mindful of the processes that are being represented in the models and what their limitations are. Nonetheless, these also would improve physical realism, and the information would be made available to people, general people, decision makers, industries, corporations, energy companies, whatever. Quality of the data has to be good. Quantity, accessibility are always important. And of course, doing these what if scenarios are critical as well. It can both monitor and predict, even on multi-decadal time scales, to account for natural, for example, volcanoes, and human, for example, land use change, emission perturbations. So the big Tonga emission that happened is being monitored closely for all kinds of perturbations it generated recently. And it could be done beautifully in a digital twin model. It can operationalize the assessment of model processes, process errors through weather prediction techniques, and constrain missing physics through observations and machine learning. So it's envisioned that it's not just a typical weather model running as usual with all the first principle equations for momentum, energy, water and mass balances and so on, but also ingesting data and doing data-driven modeling as a combination of the dynamic modeling and machine learning approaches. It can evaluate the information content of observations and help optimize entire observation networks. Obviously, with a limited it's often zero-sum game. The more money you put in one direction, the less money you may have in other direction. So ships, for example, are slow moving, and there are very few numbers in very few in number, considering the area that we have to cover. On the other hand, satellites only measure the surface, and they can only cover they cover the globe, but often they can be very different value of the data in terms of what the ships can observe in terms of, let's say, the ocean profile, for example, of temperature, salinity, and so on. So optimization of observation networks is a ongoing task that's going on for a long time. Many of you may know the Tropical Ocean Global Atmosphere Array that was started in the late 1980s is now being planned to be replaced by something much more modern, TEM TPOS, the Tropical Pacific Observation System, for example. The digital twin architecture sits much closer to the user in this sense if it is implemented successfully. It provides a framework for optimization, whether that be of disaster prevention or adaptation strategies. This can be done at scale across sectors from food, energy security to coastal protection. So you are now talking about the digital twin model that's constantly feeding useful, usable, actionable information in every aspect of policy and decision making. So learning by doing becomes much easier in this case. It gives non-experts full access to data and data analytics toolkits using a scalable cloud-based infrastructure. So all the data will be put in the cloud, and anybody can go and look for whatever little thing they may be looking for, whatever big thing they may be looking for. It represents high impact events at scale and in terms of quantities that users are already familiar with. So represents high impact events at scale, so that when you have Pakistan floods with all its details at village level has to be looked at, and people have to be rescued, protected against vulnerabilities, have to be understood at those scales, risks and exposures and hazards and so on and so forth, and responses have to be devised based on those as well. Okay, so the quantities that users are already familiar with will help by giving them in this digital twin, whether it's waterborne disease, early warnings that are issued by the local agencies, or evacuation plans, and so on and so forth. Okay, just to touch on the big data challenges in the geoscientific context that just was mentioned from this paper here. This is a very broad schematic where we are looking at data size which now exceeds 100 petabytes, and it's growing quasi-exponentially. Tapering of the figure to the right indicates decreasing data size. The speed of change exceeds 5 petabytes a year, and data are taken at frequencies of up to 10 hertz or more. Reprocessing and versioning are common challenges. So even as many billion data points come in every morning to feed the weather forecast models and climate forecast models, for example, often significant fraction, maybe even majority of the data can be rejected by quality control issues in terms of what the data, what the models can actually ingest. So data assimilation methods themselves have to improve dramatically and develop new approaches to reduce data rejections and to include human data as well in a digital twin world. Data sources can be 1 to 4 dimensional, spatially integrated from the organ level, such as leaves, to the global level. Earth has diverse observational systems from remote sensing to in situ observation. The uncertainty of data can stem from observational errors or conceptual inconsistencies. So just look at this phase space. Observed and simulated big data. Volume of data size matters, velocity, speed of change of data, variety, so diverse data sources, and veracity, uncertainty of the data. So they increased the knowledge from data to go after patterns and knowledge, so small and digestible organization of data, real-time critical in some areas but not in all, integrated across disciplines, and confidence robustness. So then it feeds back to data from knowledge, so you have to then twinkle your observational network, optimize it, and so on in this digital twin, for this digital twin world, but especially for in general the machine learning AI approaches to improving forecasts, producing newer products that are more local specific, region specific, sector specific, event specific, and so on. So can all these be combined and a digital twin be produced successfully to manage the human activities, human natural interactions better, so that we continue to do experiments more carefully and know their impacts often, as often as possible before they happen. The digital twin obviously can allow us to do this, and when it will be implemented in a couple of years, we will see how many new things come out of it in terms of new insights, and then how system can be constantly updated and then used for not just Europe, which is funding it right now, but for the rest of the world. Okay, so it's just another exciting advancement in the kilometer scale modeling, going from ocean and climate to digital Earth. And these digital twin is envisioned to run different aspects of the Earth system for different time scales, spatial scales, different days, years, different time horizons, and so on. So it has infinite possibilities in theory. So let's wait and watch how it evolves. Okay.